introduction. Alright, so this is the Benford's law talk. And so I know some of you have heard this before, but I will talk a little bit differently to get to some of the fragmentation problems and try to give a sense of some of the algebraic structures. I will decrease the selling of why we care about this for the applications, but I will leave the slides there so if you want to, you can look at them. So the motivating question is you observe some set of data and you want to understand the distribution of the leading digits. And so a lot of times you might just guess, well, everything is equally likely. Maybe it happens 10% of the time as a 1. Then you realize the leading digit won't be a 0, because if I write in scientific notation, even if it's 0.00053, the first digit is a 5, so you correct to 1/9 or 11%. It turns out for a lot of things it's about 30% for 1 and about 4.5% for 9, monotonically decreasing. So lots of different systems. Fibonacci numbers. Very easy to show Fibonacci numbers satisfy Benford's law. Most common iPhone passcodes, I would prefer not to mention where this data came from. Twitter uses by number of followers and distances of stars from the Earth. So lots of different data sets in many different realms satisfy something like this. So the question is, why do we have such universality? So I'm going to explain why this is happening, talk a little bit about applications, and discuss some open problems. So the caveat I love, and I actually emailed Scott Adams, I love him, to get permission to use this. So Dilbert's travel expenses are rejected because all of his meal costs are round numbers. He's a liar or worse. I decide what to order based on what totals to a round number after a 15% tip. That's worse. Just because something is unlikely doesn't mean that something fraudulent has happened. There could be another alternative explanation. And for those of you who read Dilbert, this is not that surprising considering other things that happen in the strip. All right, lots of different examples of where Benford can follow. Some applications: analyzing round-off errors in computer science, determining optimal ways to store numbers, and detecting fraud, either image fraud or tax fraud. Benford's law is another way of dealing with the fact that human beings are terrible at making random numbers or doing things randomly. We put in too much structure, we omit certain structures. So general theory. So for a lot of things, we talked about this last time, the probability of a first digit being 1 is about 30%. It's explicitly log base b of d plus 1 over d. So what's going on? So has everybody here, other than myself, taken a class in abstract algebra or group theory? Okay, good. So I am the only one who has not taken group theory. You haven't? Okay. But you took number theory with me, so we've already covered the stuff you need. I've taught group theory twice, so it's okay. So we say A is equal to B mod C if A minus B is an integer multiple of C. The significand, we talked about this yesterday, is some number between 1 and the base times 10 to a power. Two numbers have the same significands if and only if they have the same leading digits. The key observation is the log base 10 of x is the same as the log base 10 of x tilde mod 1 if and only if they have the same leading digits. And the reason is when you take the log of this base 10, you'll get a k. And then when you look at it mod 1, since k is an integer, k will vanish. So what this means is that if we want to understand the leading digits, we do this transform of our data. We take the log base 10 and we look at that mod 1. So if you're thinking about this, you might remember e to the 2 pi I of u is cosine 2 pi u plus I sine 2 pi u. If I increase u by an integer, I don't change the value because I've just increased by an integer multiple of 2 pi. Most of the time, if you take your function and replace your quantity with just its decimal and just chop off the integer, that's going to matter. If you look at your bank statement and the bank decides to just give you whatever decimal fraction you have and keep the integer part for themselves, you're not going to be happy. But for this function over here, you won't notice a difference. Okay, so equidistribution. We say a sequence is equidistributed mod 1 if in the limit the probability it lies in the subinterval is just the length of that subinterval. So if I have an interval from 2/3 to 1, I should be in that about 1/3 of the time. So if beta is irrational and beta mod 1 is equidistributed, this is a deep theorem. If beta is rational, there's no way this could hold because you'll just keep getting the same multiples. We talked about 1/5, 2/5, 3/5, 4/5, 5/5, which is 0, 6/5 is back to 1/5. So you'll just keep cycling among them. It's kind of nice, it's a lot of math today, to see the same things coming again and again and again. So you have to have at least one proof in a talk. I don't know if I've proven anything yet today, so I can get something proved before lunch. Let's prove the log of 2 base 10 is irrational. As an exercise, I would leave the golden mean to you. So assume the log of 2 base 10 is rational. I can write it as p over q. I exponentiate to get 2 is 10 to the p over q. Well, 10 last time I checked was 2 times 5. So I get 2 to the q minus p is 5 to the p. The only way this can work, I can assume p and q are relatively prime, is p must be 0 and then q minus p must be 0. So the log of 2 base 10 equals 0 over 0. Okay, so the log of 2 base 10 is irrational. What this will mean is that if I look at n log 2 base 10, that will be equidistributed. Okay, so I chose one of my favorite irrational numbers, the square root of pi, and I looked at n square root of pi mod 1 for n less than or equal to 10. Does this look equidistributed, yes or no? Yeah. Does it look perfectly equidistributed? Would you have expected a better fit? No, in fact, if I had a better fit, I would have been deliberately choosing the number to get a good fit. I shouldn't have exactly one in each box. That would seem a little suspicious. I want something with a little fluctuation, but not too much. Here's n root pi up to 100, up to 1,000, up to 10,000. And at this point, if you have really good eyesight, you can see some small fluctuations, but it's getting really hard. All right, so the fundamental equivalence is a data set is Benford if and only if its logs mod 1 are equidistributed. And here is the simple proof. We talked about this expansion before, and here's my numbers 1 to 10. We wrote this yesterday. Here's 0 to 1. If I have a number whose first digit is 1, then when I look at it on a log scale, the log of 1 is 0. The log of 2 is about 0.3. It's the log of 2 base 10. So I would fall here about 30% of the time. So this is giving me my 30% here. If it's easier to rotate it 90 degrees, by all means look at it this way. And you can see if I want to be a first digit of 5, I've got to be between 5 and 6. And that's going to move over here to these two numbers. And this is where all the probabilities come from. Okay. So continuing, let's show 2 to the n is Benford base 10. Can you give me a base where 2 to the n will not be Benford? 2. What else? 1. What else? It's not Benford base 2. It's not Benford base 1. Not Benford base 4. The log of 4 base 2 is going to be rational. So if your base is a power of 2, it's not going to be Benford. Other than that, it'll be Benford. And the proof is just, well, the log of 2 base 10 is irrational. So if I look at 2 to the n, if I look at the logs, I get n log of 2 base 10. N log of 2 base 10 is uniformly distributed, so it becomes Benford. All right, Fibonacci numbers are Benford. The simple proof, here's the recurrence relation. I guess a of n is r to the n. I then find that the roots are 1 plus or minus root 5 over 2. It turns out if you have a solution, I can multiply the solution by constant, and it's a solution because it's linear. I can add 2 solutions, and it's a solution because it's linear. So this is Benet's formula. We talked about it last time. The general form is the following. This is less than 1 in absolute value, so as n becomes very, very large, this becomes negligible. And now all I need is essentially that the log of the golden mean is irrational. The square root of 5 just translates things, not a big deal. And then you just do a small amount of bookkeeping. Most linear recurrences are actually Benford. an plus 1 is 2an. That's what we looked at before. And this is a nice way to lead up to the Zeckendorf stuff later. Now if I do 2n an minus 1, it's a little bit more interesting. If I choose a0 equals a1 equals 1, what's the next term? So the first two terms are 1. What's the next term? Try again. 1. 2 times 1 minus 1 is 1. In fact, what's every term of the sequence? Every term is 1. If I take a0 is 0 and a1 is 1, then I get 2 times 1 minus 0 is 2. Then I get 2 times 2 minus 1 is 3. Then 2 times 3 minus 2 is 4. So I'll leave it to you as a nice induction. You actually get the numbers 1, 2, 3, 4, 5, and so on and so on. What's going on here is this has a repeated root, and the root is 1. A root of 1 is the one thing that will kill you for Benfordness. Okay, so let's look at digits of 2 to the n. Often the rate of convergence matters. So I calculated the first 60, but because the numbers are getting large, I'm only going to display the first 30. So here's how often I have each digit. Here's the theoretical predictions. Here's the observed values. Good fit, bad fit. What do you think? Yeah, it looks pretty good. Where's the main issue? Which is the worst number? So is it 7, 8? There's one other candidate. 9. I would say 9 is the worst because if you look at the percentage difference between the observed and the predicted, the percentage difference is the largest. But the number of predictions, it's smallest for these values. So maybe we just haven't gone far enough. This is the big question we always have. So I'm going to say that this is the bad. There is an explanation as to why things are converging so slowly. Who here is a scholar of classic languages? Oh well. Who here has some knowledge of prefixes? All right. How many megabytes are in a gigabyte? 1,024. If the computer scientists truly cared about ancient languages, there'd be 1,000 megabytes in a gigabyte. Do the computer scientists just have no knowledge of classics? Yes. That's outside of my jurisdiction. I cannot prove that. But computer scientists do have knowledge of computers. And they know base 2. Base 2 is great. 2 to the 10 is 1024, is almost 1,000. So with a reasonable abuse of notation, the computer scientists will say, we'll go from megabytes to gigabytes. They do have 1,024 megabytes in a gigabyte. So if you actually look at downloading a very large file, if it's getting close to a gigabyte, you can see the number of megabytes getting very close, then 900 then drops onto like 0.999 in terms of how it's doing things. What would happen if the computer scientists had exactly, what if 2 to the 10 was exactly 1,000? Then every time I increase my n by 10, I would return to where I started, padded by 3 zeros. And I would not expect to get Benford. Whatever my initial numbers would be, I would just keep padding by 3 zeros. But because 2 to the 10 is not quite 1,000, it's slowly going to start becoming Benford. We never see a number that starts with a 7. It's going to take a while. The 64 will eventually get up there. But you can see how slowly these things are moving, and it will take a while. But then once it's 7, it'll stay at 7 for quite a while and make up for it. And in the limit, everything will be okay. But it takes a while. So here are 3 of my favorite numbers: the Euler-Mascheroni constant gamma, the Euler constant e, and pi. And so what I'm doing is I'm calculating chi-squared values. I'm seeing how good is Benford to these numbers. The smaller the chi-squared value, the closer Benford is to describing what happens when I look at powers of these numbers. So this is now time to play Sesame Street. One of these numbers is not like the other. One of these numbers just doesn't belong. Pi. Pi starts off really bad. The chi-squared value should be at most 15.5%. It's really bad, but then it starts coming down and gets really small. Okay, but then it gets up again. Then it goes down. Then it gets up again. What's going on with pi? So who here can rattle off digits of pi? Can you give me 20? Okay. All right, I'll trust you. Okay, I'll trust you. Okay. Who can rattle off digits of pi squared? Sometimes I get 9. Yeah, okay. So basically, you learn digits of pi and then you stopped. I mean, there's infinitely many more powers, right? So I'm assuming nobody can do pi cubed if you can't even do pi squared. Yeah, I mean, this is. So I'm now looking at plots of the chi-squared values for pi to the n, which is red, and e to the n, which is blue. Anybody notice anything about the red versus the blue? Red looks periodic. Any rough guess as to the value as to what is the period? Pi. Pi is 3.14. All right, so about 175 for the period. And then each one of these heights is a little bit smaller than the previous. All right, I was asking you about powers of pi. You should really, you should have done this when you were younger, but pi to the 175 is about 1.0028 times 10 to the 87. So every time you increase pi by 175, you are essentially almost padding by 87 zeros. Not quite, and this is very similar to the 2 to the n, with the 1024 not quite being 1,000. But now we actually have 1.0028. It's a little bit better than 1.02. And this is why you're getting something that essentially looks like 175 for the period. Good observation. So why do we have Benford in so many places? So let's imagine you have a street where the houses are labeled 1 to L. If you stop with L as 199, you just went through 100 streets with the first digit of 1, you'll get about 5/9 of the streets have a first digit of 5/9 of the houses have a first digit of 1. If it ends with 999, you just went through a huge number of non-1s. So it's going to fluctuate between 1/9 and 5/9. And so, if I plot this as a function of the length of the street, it's going to look like this. If I do a logarithmic change of variables and plot it versus the log of the street length, now it looks a lot more periodic. Benfordness occurs the more averaging you do. What if we have lots of streets of different lengths? So here is just all houses. Each street is going to be from 1 to 10,000, and I'll have 1,000 streets. So I get basically a uniform distribution for how often I have each digit. Now let's have it a little bit random. I'm going to choose randomly a number from 1 to 10,000, and that will be the length of my street. And then I'll take all the houses, and then I'll choose another number randomly, and I'll take all those houses. And if you look at that now, it's not Benford, but it's closer. If I do it again, random, random, it's closer. If I do it again, random, 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 it's really close. And so the more processes you have going on, typically the more Benford something becomes. So quick probability review, area under the curve is the probability I take a value between those events. P of x is non-negative, it integrates to 1. The mean is x p of x, the variance is how spread out you are. Independent knowledge of one gives you no knowledge of another. So the central limit theorem, we talked about this last time, is if I take a sum of independent random variables, I subtract off the expected value, and I divide by the standard deviation, this will often converge to being normally distributed, with mean 0, variance 1, because of how I've normalized things. So let's look at a uniform distribution adjusted to have mean 0, variance 1. Does that look like the bell curve? Does that look like a normal? No, but it's not horrible. Now if I sum two uniform distributions, this is the triangle you get from rolling die. If you have two fair die, you get a sum of 2 and 12, 1 out of 36 times, and you get a sum of 7, 6 out of 36 times. So the triangle is not that bad from a normal. If I do 4 times, it's getting pretty close. If I do 8 times, it's getting even closer. If you wanted to, here is the explicit formula for the density of a sum of 4 uniform random variables. And this tells you why we like the central limit theorem. You do not want to work with this. And you really don't want to work with the explicit density for the sum of 8. It's much nicer to be able to say, oh, it's approximately normal, and let me control the errors, and let me work with that, rather than working with this horrendous nightmare split. So here is looking at a normal distribution mod 1. So a lot of processes, their logarithm becomes normally distributed. And if the logarithm is uniformly distributed mod 1, then you get Benford. So what I want to see is I want to look at what happens to a normal when I look at it mod 1. And let's say the normal has growing variance. Let's see what happens. So here I'm looking at a normal, mean 0, variance sigma squared. Let's say the variance is 0.01. If the variance is 0.01, that means the standard deviation, the square root, is about 1/10. It means I really want to be close to 0. I want to be essentially between maybe minus 0.2 and 0.2. And if you look at the density, I'm essentially between minus 0.2 and 0.2. Because negative 0.1 is the same as positive 0.9 mod 1. So does this look uniformly distributed when the variance is 0.01? So here's the uniform distribution. Does this look close to uniformly distributed? No, not even close. What if I increase the variance to 0.1? It's better. What about now? Look at the axes. Look at the axes, right? The axes go from 0.9990 to 1.0001. So when you look at the axes, it's very close to being uniformly distributed. Okay, always check the axes. Okay, if you learn nothing else today, be aware of the axes. And when you are writing papers, make sure you have your axes labeled. Make sure you have good notation. Journals will often tell you to redo images, and it can be a real pain to have to redo images after you've already done the work. You want to make sure you save your data in good ways. If the code is not that long or involved, what I often do is I put the code in my text file and I comment it out. So if I have to regenerate an image, I've got it right there. It's extremely useful. All right, so Pavlovian response, see a product, take a logarithm. So let's say you have a bunch of random variables and you look at their product. I'll show you that this is often going to be Benford. So let's let yi be the log of xi, so vn is going to be the log of the product. So vn is the log of the product, so it's the sum of the logs. Well, by the central limit theorem, if these are nice, these will converge to being a normal distribution with growing variance. And a normal distribution with growing variance, it's a nice calculation, becomes uniformly distributed mod 1. And this gives you some sense of where the Benfordness is coming from. It's a nice calculation. Applications. Anybody know who this person is? Stephen Miller, former Commissioner of the Internal Revenue Service. He chose whom to either audit or slow down in terms of applications based not on financial grounds, but based on political grounds, and ended up losing his job. So you've got to be very careful how you make decisions. So I talked about this audit of a bank that had a huge spike starting with 4, with 4.8, 4.9s. We talked about this yesterday. What was happening was a person was having their friends get $4,000 in charges, $5,000 in charges. That was below the threshold needed for an internal investigation. The friend could just write it off, and this was a nice way to steal money from the bank. It was caught with Benfordness. Stream flow data, applications. Here's one of my favorites. Isn't this a beautiful picture? Nice tree, not raining, sunny day. If you've seen this before, you're not allowed to answer. Can anybody see the cat in the tree? Here's the cat. What you can do is you can hide a low-res image in a high-res image. So each pixel is a triple of red, green, blue. So let's say you often write numbers from 0 to 255. You write them in base 2. If I change the last 2 digits of a number base 2, is it going to change the color by that much? So what I do is I do a low-quality image where the numbers are just either 0, 1, 2, or 3. 0 would correspond maybe to 0. 1 is maybe I'm going up 64. 2 is 128, etc. And what I do is I change the last 2 digits of each pixel to be the corresponding digit for the cat. And now I can hide the image of the cat in the image of the tree. It'll be a slightly lower quality image, but you can actually have messages written. It doesn't have to be a cat. It could be a real just text message. And in fact, in terms of the quality of the image, some of the pixels will actually be right anyway. So there's a lot of stuff you can do in terms of hiding messages. Benford can often detect when something has been modified. All right, what I want to do now is I want to talk about stick decomposition and 3x plus 1. So consider a stick of length L. I'm going to uniformly choose a proportion P in 0, 1. It doesn't have to be a uniform distribution, but let's do uniform for now. I'll get 2 sticks of length P times L and 1 minus P times L. And then I'll break each of those sticks. Maybe I'll choose another random number in 0, 1 from the uniform distribution. And I'll have a fragmentation problem. Or maybe I'll use the same probability P every single time. So if I do the same P every single time, it makes things a lot easier. What value of P might cause trouble? 0, 1, and there's one other value. 1/2. Because if it's 1/2, every fragment is going to have the same length. So the conjecture was, as long as you don't do anything stupid, you don't choose 0, 1/2, or 1, you'll get Benford. And here's what we got from using 0.51. Does this look Benford? I think so. Counterexample, take P equals 1/11, and you will get something that's not Benford. So what's going on? So let's look at the different possibilities for the stick lengths. So you'll have P to the n minus j, 1 minus P to the j. Well, I can write this as P to the n, 1 minus P over P to the jth power. And so when I do that, when I go from one length to the other, one length is going to be P to the n, the other length is going to be 1 minus P to the n, and I'm going to multiply by a factor of 1 minus P over P. If 1 minus P over P is a power of 10, then they all have the same leading digit. If 1 minus p squared is 1 minus p over p squared is a power of 10, then every 2 times I get back to where I started. So I want to make sure that 1 minus p over p is not a power of 10. So if 1 minus p over p is 10 to the y, where y is rational, I'm going to get non-Benford behavior. And then if it is irrational, then you will get Benford behavior, and you can actually get things about rates of convergence. And so I'm not going to go into too much detail here. Here's, p equals 3/11. I get the log base 10 of 8/3. This is irrational. I'll get Benford. I take 1/11, and then 1 minus p over p. All right, so 1 minus 1/11 is 10/11. Divided by 1/11 is 10. That is just 10 to the first power. And you can see quite clearly, the spike of what's going on in the non-Benford behavior. Here's another fun one. 1 plus 10 to the 33/10 reciprocal. Another nice rational process. So we've done a lot of work on decomposition problems. We've found ways to handle dependencies. This is just one of many problems. Handling dependent random variables is very difficult in general. And you have to find ways to count the dependencies. So if you're interested, we have some stuff on that. I want to just talk a little bit more about the algebraic structure of numbers and how this comes into play. So 3x plus 1 problem. Two of my favorite quotes. One is by Kakutani, that when he traveled across the country, whenever he told people about the 3x plus 1 problem, they go, oh, this isn't so bad. And they'd spend about a month working on it and then give up in frustration. The great Paul Erdős said mathematics is not yet ready for problems like this. 3x plus 1 turns out to be connected to so many things we can't do. So if x is odd, we multiply it by 3, add 1, and then we remove as many powers of 2 as we can in one step. It's just a faster way of defining things. The conjecture is for some n, no matter what number you start with, eventually you will iterate to 1. So if we have 7, we can just keep iterating. And these subscripts are telling us how many powers of 2 we pull out. So this is called the m-path. And so, I can look at all numbers whose m-path starts off with a 1, 1. What numbers have this form? What numbers have 1, 1, 2, 3, 4? And here's a heuristic proof of why the 3x plus 1 conjecture is true. Don't really want to go into that now. This is the result I proved with Alex Kontorovich, who'll be speaking at YMC. And then this was generalized by 2 professors at Michigan when I gave the talk there. We showed that as m goes to infinity, x of m is where you are after m iterations. This is where you expect to be, 3/4 over m to the x naught. So we looked at the ratio of where you are to where you expect to be, and we showed that that converged to Benford. What they did is they looked at a huge number of starting seeds, and they showed that almost all starting seeds, after you do so many iterations, if you look at the values of the iterations, they will be within a certain tolerance of Benford. So how does the proof go? The main idea is you start off with what's called a structure theorem. You want to look at the number of numbers that have a given m-path. And it turns out that if you want to have an m-path of k1 through km, it's given by an arithmetic progression that's full. It starts off in the very beginning. You don't have to wait, well, how long do I have to go before I get the first term? It happens very quickly. And so what Yakov Sinai and Alex Kontorovich showed is that not just for 3x plus 1, but for more generalizations of this problem, it looks like these ki values are independent, identically distributed geometric random variables with parameter 1/2. And so we can convert what's going on to some probability questions. And so I can ask, how often I want to look at where I am versus where I expect to be. So if I let Sm be my sum, I can look at how often is it different from my expected value, and then you just start playing some games. And then it turns out I want to calculate this probability. I've got sums of geometric random variables. I can calculate what this quantity should be. It turns out that, as I mentioned last time, the fact that this is discretely supported causes an enormous number of challenges. How can we get around this? Well, we can get around this by being a little bit more careful, and we need something called quantified equidistribution. So I said before, if alpha is irrational and alpha mod 1 becomes equidistributed. Well, how quickly? What's your error? And this is where the algebraic structure of the number comes into play. So if I'm not going to go into too much detail here, there's something called the irrationality type. Did I do it on the previous slide? No, maybe not. Maybe it's on the next slide. So the irrationality type, we say number has irrational type kappa if kappa is the supremum of all gamma such that q to the gamma plus 1 times the minimum over p of alpha minus p over q equals 0. Okay, what does this mean in English? I have my number alpha. I want to find the rational with denominator q that's closest. So choose the p that's closest. I should be able to get to within 1 over q. That's not that hard. I move in steps of size 1 over q. So getting to 1 over q is not too bad. Dirichlet showed that if you're irrational, you can get to within 1 over q squared, essentially. You can do a little bit better, but essentially 1 over q squared. What if you can do even better? What if you can do 1 over q cubed, 1 over q to the 4th? That means you can approximate it extremely well by rationals. It turns out if you can approximate it arbitrarily well by rationals, the number must be transcendental. And so this is just related to how close you are. And it turns out that this equidistribution, I want to know how often am I in this interval. If I have m terms, then equidistribution says it should be m to the b minus a, the length of the subinterval. And then the error term is 1 plus epsilon minus 1 over the irrationality exponent. Epsilon is free. As long as the irrationality exponent is finite, I just choose epsilon to be sufficiently small, and this number will now be an exponent less than 1, and there is a power savings. So you just need a finite irrationality exponent. For what's going on with Benford's law, I need to know the irrationality exponent of the log of 2 base 10. You could do better. I had no desire to do better. I was careless. I used a great result by Baker, and I get that the exponent is at most 1.2 times 10 to the 602. This is the largest finite number I have used meaningfully in any of my papers. 1 over 10 to the 602 is a finite number. I have a power savings, and everything works. And then there's some beautiful results that allow you to translate this into estimations. I'm not going to go through this now. I'm more interested in these fragmentation problems. I will just put these slides up here so you can pause if you're really interested. This is just showing you, prediction between theory and experiment. So it's actually very easy to look at a 10,000 or 100,000 digit number, because all we're really doing is multiplying by 3, adding 1, dividing by 2. You can represent it as a list and then just do operations on a list. It's not that bad. You can also look at pulling out not all the powers of 2 at once, still good fits. You can look at 5x plus 1, again, great fits. Conclusion, we want to study other kinds of fragmentation problems. The key ingredients is taking the logarithm. It's always about what is the right way to look at things. I will just end, there's some slides on references, more references, lots of references. The Riemann zeta function and Benford's law. We should try to tie everything we've done together. Isaac Asimov did this beautifully with his science fiction writing. I will try to do that with our morning session. Zeta of S, we've seen this before, product over primes. You might recognize these slides. Here's the geometric series formula, unique factorization. This gives you the proof of the product formula. You have to be a little bit careful about convergence, so do things when real part of S is greater than 1. Properties with primes. If you take S going to 1 from above, 1 over n to the s converges to the harmonic series which diverges. There must be infinitely many primes. If you take s equals 2, it turns out the sum of 1 over n squared is pi squared over 6. If there were only finitely many primes, you have a finite product of rational numbers. What's the finite product of rational numbers? Rational. So there must be infinitely many primes because pi squared is irrational. So I actually wanted to see, could you get an estimate of how many primes there are up to x by using this? If people are interested, I can share my preprint. The original proof I got is not as good as Euclid's estimate, which gets you log x primes up to x. And it turns out, I didn't realize this, but I was using a paper that had the irrationality exponent of pi squared over 6, which assumes the prime number theorem. So by using the prime number theorem, that there are x over log x primes up to x, I'm able to show that there are almost log x primes up to x after a few pages of work. Not a very exciting result. So the next thing was to actually go through and look at the paper that proved the irrationality exponent of pi squared over 6 and see where did they use the prime number theorem and remove that and then do a better job. And so I can get that there are almost x over log x primes infinitely often up to height x, by just doing these elementary arguments on irrationality exponents. So let's look at values of the Riemann zeta function. Let's look at it at discrete sets. And so I forget if the diamonds or the stars are Benford or the Riemann zeta function, because the fit is this spectacular on the critical line. So again, it's why is this happening? This is the stuff with Hedgehog and whatnot. So we say an L function is good. We have wonderful terminology if it has an Euler product, if it has an analytic continuation with a functional equation, if we have some control over the size of the Fourier coefficients. We basically want some number aleph log x. We have some control over the size of these numbers. We want them to be of size 1 in these product expressions. This is an analog of the Riemann zeta function. It's a weaker form. This is what I was telling you about yesterday. We want good estimates for the cardinality of the empty set. We want the empty set to have not too many elements. Okay, the Riemann hypothesis is enough to allow you to bypass this. And so it turns out that these properties are known for certain families of L functions, in which case we can then prove that we do have Benford behavior. And so the key result is the log normal law of a couple of people, which says I want to look at the measure of the values of t between 2t and 2t, says that the log of the absolute value of my L function is in this interval. It converges to being normally distributed. One of the things that's a real pain is that the probabilists and the number theorists use sigma for two different things, and you have to decide who do you want to piss off when you write this paper. Do you want to piss off the number theorists or the probabilists? I have been trained, I have to use sigma as the real part of S. I cannot change that or I will be in trouble with my advisor. Now, if you think about it, writing S equals sigma plus IT is a bit strange because you're writing S as a Greek letter plus a alphabet, Roman letter. What I have heard is the following. Until you prove the Riemann hypothesis, you will use Riemann's notation. If you prove the Riemann hypothesis, you may make everybody use whatever notation you want. So you use sigma plus IT. And so then, what Alex and I were able to prove is that if your L function is good, your Benford, and lots of nice results going in here, it's the method of moments again. This is what we were doing when we were studying random matrix theory. We were calculating moments. Calculating moments is a great way of showing what's happening. And then we're able to calculate these things so it converges, becomes uniformly distributed. All right, so this is a good place to end for the morning. I'll hit stop.